Hello and welcome to the astrO podcast. My name is Oindrila Majumdar, and today's episode is actually going to be a little bit different. We're going to be stepping away from the world of astrophysics and into a much more deeper thought, the world of pure and abstract mathematics. Now, mathematics is more like a language in science, and it helps us to give us a deeper way of thinking in structures, geometry, uncertain events, and also the financial market. And for us to understand these, it's kind of a tool in understanding uncertain times through probabilities and predictions. And to help us understand and explore these topics, I'm joined with Professor Emeritus Freddy Delbaen, who is a distinguished mathematician and has served as a professor at ETH Zürich and has had huge contributions towards the probability theory and basic fundamental mathematical tools to understand uncertainty, risk in financial markets. Welcome, Professor Delbaen. How are you today?
I'm fine, thank you. I'm happy to be here. Thank you.
It's great. So today's beginning, I actually wanted to start off a little bit differently. And I wanted to first understand your journey of mathematics and how you came into the field. So you were born in 1946, which is a little bit after the end of the World War II. And the world was kind of in an economic uncertainty, a social crisis. And actually a lot of remarkable mathematicians were also born around that time, like Pierre Deligny or Georgi Margulis, who are also field medalists and Abel Prize winners. So I wanted to get your point of view. Like, do you think that during these episodes, like these uncertain times, do you think that like in these intellectual environments that it could influence your imagination or curiosity of mathematics? Or were you more like influenced by your collaborators or contemporaries?
Oh, I guess that after the Second World War, there was a revival of studying mathematics. And so this generation profited from this revival, and a lot of new mathematics was developed at that time, or that kind of mathematics existed, but its development was halted because of the war. So after the Second World War, there was a huge development, and that triggered a lot of people to go into mathematics, and that in fact contributed to the education of a lot of people. So that is the reason why so many mathematicians were born. So many people who were born after the Second World War went into mathematics. And or physics as well.
Yeah.
Yes.
And also, like, the economy was at such an unstable time that they actually needed like new things to stabilize the economy, like mathematical tools.
Well, there was, especially in Europe, there was the economy was down, of course. There was nothing left after the Second World War, and there was the Marshall Plan that contributed to the revival of the economy in Western Europe. And also there were some social developments that made that more people had access to higher education.
Yeah.
Before the war, higher education was reserved to, let's say, a very limited group of people, namely those people who could afford it. But after the Second World War, because of the social developments, many more people could afford to send their children to higher education. So there was, of course, also the baby boom in that time. Many people, many families had children after the Second World War, so the baby boom in the 50s, the beginning of the 50s, and that also made that the universities were growing.
Yeah.
So not immediately, of course, but say
Eventually.
15, 20 years later. So there was a huge influx in the universities. So that means that also the selection became better.
Yeah.
And so in any field, and that also had as a consequence that there were more math students, more physics students, more science students, and so on. So that is.
So there were like a lot of factors that contributed to.
Well, I wouldn't say it's fashion. It is because there were some people liked mathematics but couldn't succeed. Some people liked to go to the university but it didn't work out, and so selection was good. Many people who started mathematics dropped out, of course. That is what it means. In the university, that's the way it works. Huh? That is not everybody who goes to the university ends with a degree. We have to accept that.
So moving on, so the world knows that Jean Bourgain, who is a very famous field medalist, was also your PhD student. And, you know, students always, you know, make their teachers very proud. So could you share a little bit of like your experience on what it means to see your students at such extraordinary heights?
Well, Jean was, of course, a gifted student. From the beginning, it was clear that he was one of the best mathematicians that Belgium had at that time. And so I was very happy to have him as a master student and then later as a PhD student. He learned very quickly, and I must admit that after a while I learned more from him than he learned from me, so that is clear. And but that is one has to accept that. I had a talk with one of my colleagues in mathematics from Poland, Oleg Pelczynski, who had a great influence on my mathematics development. And he told me that, see, if a mathematician or a university professor has a student who is better than himself, he has the right to return, to take pension. And if he doesn't have a student who is better, he should stop doing mathematics. That was his saying. And so for me it was good to have Jean as a student, to learn more mathematics from him.
Okay.
I remember that I was working since many years on a famous problem, and I was not the only one working on this problem. There was a whole school of mathematicians working on that kind of problems, and a solution wasn't found. And so one day Jean came into my office and said, "Well, what are you working on?" So I told him, and then he looked at me, he returned to his office, and after 10 minutes, well, maybe a quarter of an hour, because he had to finish his coffee, he came back and he said, "Well, I will make a counterexample to this." When I told people that he could solve this problem in 10 minutes, nobody believed it, but it was true. This is, he came up with the idea, and the next day we worked together on this idea, and then, yeah, we pushed it further and looked at all the consequences it had. So it was amazing that this guy was able to solve a problem in 10 minutes, looking at the right approach. And many people have been working on that topic. And many famous people, in fact. it remained open all the time.
Well, that's really like interesting.
It was, yes. When I told that later, they said, no, we don't believe it was in 10 minutes. I said, okay, let's make it 15 because he had to finish the coffee.
Well, I also wanted to understand more of, your core work in mathematics. And I had two questions. So one, your core work, and also like in the future, I aspire to be an astrophysicist. And I also want to kind of understand like how else do we need like applications of mathematics, because it's not like for us right now like as students it's just to pass exams and get through school, but I feel like nobody actually, like no students understand that how would we use math in real life, because that's everyone's question. Like a lot of people in my class will always ask me like, why do we even need math, we're never going to use it in the future. But in reality, like in this rising age of AI, I think it's very important for us to understand it. So those are my two questions. One is like, why do we need it? And second, what is your core area of mathematics?
Well, I see that you have a nice cell phone with you, and you see each time you use your cell phone, you are in fact using some tricks from mathematics and some area from mathematics called wavelets. This is built in all kind of software that is present in this cell phone. And wavelets were developed by another famous mathematician from Belgium, Ingrid Daubechies. And so her approach and her development contributed to what you have in your hand, as a cell phone. Your cell phone wouldn't work without wavelets. So that is also television behind you. Same thing. It wouldn't work without that. There's a whole theory about coding. Coding, when people talk about coding, they think about secret messages. But it's not only secret messages, it's just transmitting things. And, transmitting things is, we are all using cell phones, we are all using communication means, modern communication means. The coding that is behind is application of mathematics. Without these number theoretic tools that are hidden there, things wouldn't work. So we should not only look at mathematics as things that are able to calculate a couple of things. No, it's a part of real life, but it's hidden. It's hidden, yeah.
I don't think many people understand like how math is actually everywhere.
It's everywhere now, yes. Yes, it's everywhere. And you said artificial intelligence, yes, it's nice, but my guess is that artificial intelligence will have some influence on the way people will do mathematics.
Yeah, definitely.
But essentially, the big problems, in my opinion, will not be solved by artificial intelligence. No.
But it could help us, right?
Sorry?
It could help us
It can help us, and for some problems we already use computers. There are massive calculations, algebraic calculations that are done by computers, and which mathematicians would not be able to do in a lifetime. So there the computer helps, but I don't consider that as artificial intelligence. It's very important, but it's a routine that is applied. It's programmed and it's applied. It's not intelligence. It's not creative, but it helps already mathematicians. That is some famous problem for color problem was solved using a big computer program written for that, and the real contribution there was the reduction of the problem to let's say, some things that could be checked, but that could not be done in a lifetime. So it was programmed, and the computer did it. At that time, the computer needed an immense amount of hours. Nowadays, the computer would need a couple of minutes for that. But the real contribution was the reduction to something that could be checked and calculated. It could have, eventually it could have been done by hand, only it would have taken more time.
So it was more of like manual work that the computer had done.
It took away the manual work of that, yes. But now some artificial intelligence kernel bring some creativity in some problems, which is...
we were discussing that there are some AIs that like might have the way to like think with problems and not just take it from the internet and not from all the answers.
This creativity that's coming out of this artificial intelligence is not frightening. It's not frightening at all. It will help mathematicians to go deeper in the subject. I'm a little bit old, so I'm not afraid of these things anymore.
So, also I wanted, like, my second question was, you know, what field of like work do you, like, how do you use math in your field of work? I mean, you are a mathematician, but I'm saying that as in like, what is probability theory, like how has it contributed in your work?
What do you mean by that? Can you repeat?
As in like, what is your field of work in math?
Oh, well, my main interest in mathematics is probability theory, mathematical analysis, applied to financial mathematics, to financial mathematical problems. So this is my main interest, and most of the applications there are within mathematics and within modeling of problems, and most of them come from most of the applications are based on probability theory and on functional analysis. So these are the things. The probability theory is a nice field.
I actually want to get more into that as well, like in my next question. So like, can I get so I wanted to get a little bit more into probability theory because as a student, we've obviously learned probability like since grade 5 or 6. And I think now that I've come to grade 10 and things, we've learned new words in probability, like conditional probability or Bayesian theorem. And I wanted to understand, like, maybe in your definition, you know, what is conditional probability or what is Bayesian theorem or maybe what is probability in your definition?
Well, for a mathematician, probability is a mathematical object. It's a structure from mathematics, and where some numbers are given to some sets which are called events, and then there's a whole mathematical theory, and that is called probability theory. But then people try to give interpretations to that in real life, and some of these interpretations need applications, need new theorems, new approaches, which then in turn are giving problems in fundamental mathematics. And if they are solved, then the problems can be solved maybe. And all these things are, some of these concepts were introduced a long time ago. But there are also new concepts which are introduced and now contribute to real life. Whether the models that come from probability are really describing real life? And that's another question. For a mathematician, this is, let's say, in his work, this is not so important. He is more interested in the internal consistency of what he is doing. And some of the models can be applied directly, and as long as they describe the main things of the problem coming from real life, people can say we can apply it. But sometimes there are new features coming up which make that these models or these approaches are not adequate for that problem. And then people say, well, the mathematics were wrong. No, the mathematics were not wrong. Mathematics were right. Only the model that was used was not adequate for that problem. It was not describing the problem in a sufficient, exact way. That is also the meaning of probability in real life is a philosophical question. There are people who are saying, no, there is no probability in real life. There is no randomness. Everything is deterministic. This is a philosophical viewpoint. But that viewpoint does not affect the study, the mathematical study of probability theory. You can have philosophical discussions, of course. That's nice to have them from time to time. But it's not the real part of probability theory. A lot of things in mathematics are far away from reality. In high school, you certainly have seen real numbers. Did you ever meet a real number in the street? Did you ever see something where a real number really was needed? It is needed because we have mathematical models and applications of these models which need real numbers. But do real numbers exist in reality? No, they are a concept coming from mathematics, from logic. If I walk on the street, I will not meet a real number.
So you're basically saying that math, I mean, I had a later section on, math and reality, but now that we've come to it, I feel as if that you're saying that math doesn't define reality or doesn't explain reality, but mathematics has given us so many things that are in reality, like you said, the cell phone, or like how airplanes work. Like these are all given from, mathematical equations and things. And like you said, like you haven't actually seen like a real number on the street. The same applies for, general relativity, where Einstein says like, yeah, there is a fabric of space-time and I'm proving it with these equations. But when you go into the universe, you can't actually see a fabric of, space-time and how planets are warping into that fabric. So like there have been like a lot of uncertain times, for example in Dubai, like this unexpected what's happening. I feel as if the probability models that the mathematicians create, but like will predict a number of things. But when the uncertainty actually happens, a lot more challenges and predictions that the model couldn't predict like appear. So how do you think, countries or like mathematicians who want to predict certain events, how can they make it more reliable using your theories?
Well, I'm always very hesitant when people are predicting things. Mathematicians, by definition, do not have a crystal ball where they can look and then see what the future is. That's also these theories that predict things. Many of the predictions didn't come out, or they have put us on the wrong track in some sense. So mathematics, as I said, is based on logic. And in fact, it's only logic. That's it. If you want to apply it to reality, then you try to make a model of reality on which you can apply your theory. Now, if you then try to predict things, well, a lot of things that happen even today were not predicted. And it is very, and then people say, yes, but the predictions were not good, the mathematics were not good. No, the model is simply is not taking these things into account. We have no crystal ball, and so sometimes we try to put unfavorable events in the models we use without telling what these unfavorable events could be. We simply add some event and say, well, that's a bad event, and we give some probability to it. But this probability is not based on reality, it's subjective. And you can then discuss with politicians, for instance, and they will say, oh, this will not happen. This is not going to happen. I've never seen this in real life. No, it's not. We don't take that into account. Well, then a year later or so, some bad event happens, and then there is a catastrophe. Yes. Yeah.
Do you think there's like a better approach to like predicting these unpredictabilities?
There are people who try to predict events from the future, and you have these so-called world models where people, based on philosophical approaches, say, well, the world is evolving in this direction, in that direction, and then they discuss that, and then they come up with some developments, some events. And then, as a mathematician, you could try to put numbers on it, or you could try to put that in a model. And once you have put it in a mathematical model, mathematics can start working. And if you are in a mathematical model, it is easy. If you accept the model from the beginning, you have to accept the consequences. If you don't like the consequences, that's not because the theory in between is wrong. No, it's because your model in the beginning did not describe what you wanted. That is the problem. And that is also the good use of mathematics. Once your model is defined and is consistent in itself, then all its consequences you have to accept on the same basis as the start of your model. If you don't like it, if the consequences are not good and are in contradiction with reality, it's not the theory that is wrong. It's the model in the beginning that is not good enough. You have to change that. So mathematicians, what they are doing, well, they are not necessarily constructing the models, they are developing the theory to use in the models.
So on that note, as well as like, I know that in astrophysics, we also use a lot of simulations, simulations of galaxies colliding or particles interacting with each other. And I myself had also worked on a simulation a few months ago on, the Andromeda and our own galaxy colliding? Like, what would be the probability of them colliding? And there were so many research papers saying that there's a 50-50 chance, or like there's no way they would collide, or like somewhere they will collide. So I said, okay, I want to put it into simulation and see what would happen. So I had the privilege of going to NYUAD University here under the supervision of Professor Andrea, who is the department head. And he is also a numerical simulation expert. And I asked him, like, how are you putting the uncertainties of our universe, all those conditions, into just a supercomputer? And he told me the process. He was like, we put in all of the different mathematical equations or physics ideas that we base our universe off, like Hubble's law, or like the redshift and all those things. And then we just put two galaxies into it and we see what happens. But I said that our universe is so unpredictable. There are so many like new things that have happened that we thought would never happen in our universe. So how do you put that uncertainty into a supercomputer? And he said that we actually don't. We just put a bunch of parameters that our universe follows, and then we put it in. So I was like, how can that be reliable enough for us to understand what could happen in our universe after? So it's kind of relating to, what you're saying as well. So what can probability theory give that simulations can't show us alone?
Yeah, well, that's again a more philosophical question. We all these models, they obey one universal law. You put junk in, you get junk out. That's clear. So whatever you put in, the outcome is as valuable as what you have put in. Now, you were talking about physics, and I'm not so familiar with that. But the long time ago, I was present at presentation of some applications of mathematics, and that was a research colleague of mine who was working in a chemical company. And they were using the way chemical reactions work out. And of course they had parameters for that, and they had numbers for that. And before they were making an experiment with new chemicals, they have put that at that time already on a computer. Because they say, well, if the computer shows us that the whole thing will explode, it's better that we don't do the experiment. And let us analyze it again before we do something. So they were in fact simulating the whole experiment on a computer at that time. So, of course, at that time the computers were not as powerful as your cell phone. So that was not an easy thing to do. So that is but they did that. They did that, and sometimes they came up with surprising results. All models are in fact simulations of reality. When we use a model, this is an attempt to describe what reality is. So in some sense it's a simulation of reality. And if reality is obeying the equations we have put in the model, then the simulation is okay. If the parameters that we give in are possible parameters that might occur, then that means that the outcomes of the model also might occur. If it turns out that the whole thing is nonsense, yeah, well, that's because the model was not good enough. It's not because of the mathematics that is wrong. That is can it be more reliable? Well, if you want a model that's more reliable, you have to look at your problem again, at the physics of the problem, at the biology of the problem, and see what happens there. And then try to see how to translate that into mathematics.
So do you think that mathematics can give us like the best decisions when the future is uncertain?
Well, a lot of decisions are made based on models, huh? And what mathematics can contribute there is let's say, a consistency in the decisions. And sometimes it is said better to use a model that's a very, very, very rough description than to use no model at all. If you have to decide on an investment, what are you going to take into account? What are the features you want to take into account? And how are you going to do that? What are the influences of these features on your investment? And you try to describe that, and then you try to put some quantitative effects of that. And then you take decisions. If you have to take several decisions, then it's better to do that on a consistent basis. And that's where mathematics will help. If the features you have built in are not taking place or are completely opposite of what reality shows us a year later, your decisions are wrong, maybe, but at least they were consistent, but wrong. It's like gambling, eh?
Well, I mean that probabilities are mostly made from like consistent patterns that have happened, but then to predict something that like is very uncertain, like for example 2 years ago, like Dubai is known as a place where rain never happens, but 2 years ago suddenly we had flood which affected us really deeply and we didn't know how to deal with it. Or like coronavirus, like the pandemic, we didn't think it would ever hit us. So for events like that unpredictable, there's no way of predicting them, like, or using probability theories for that.
No, there was before COVID. There was nobody who could predict that such a thing or a similar thing would happen. And what you can do is you can say, well, let us make a model in which some very bad events might happen, without describing them. It's very difficult to sell that to somebody who has to make a decision.
Yeah.
Because immediately they will say, well, what kind of events you are thinking of?
But if into like one of your models, like for example, you're making a model or something, if you put in the unpredictable events that have already happened, then it could, increase like the probability of something more unpredictable happening as well.
Yeah, well, that is in finance. These models used in finance, they put in things that have happened in the past, and that's the way they do the so-called stress testing also. And by putting in these things, you have a good argument because you can say, well, these things happened.
Yeah.
Then you can make them a little bit more severe. So, well, this thing happened already, but it might be that it's something like that can happen again in a more severe way. It makes your model maybe more acceptable to the decision maker. that's one way of making models, let's say, more reliable for extreme events and so on. But we have seen that there's always something new happening.
Yeah, exactly.
That's,
And that kind of brings me to like my final question about, and like, you spent your entire life, you know, your career studying probability and uncertainty. So do you think mathematics helps us reduce uncertainty, or does it just make us realize that we need to live in a world that is very uncertain? Like, we need to accept the fact that the future is not predictable.
yeah, whether mathematics can improve, let's say, our future life and the way we cope with uncertain things, I've no idea. Mathematics tries to give outcomes or models that might help. Say, well, be careful. And a classical example is the flooding in Holland and Flanders, where many people who died at that time because of these immense floodings. The Dutch immediately reacted and they said, well, we have to build better dikes. And so they looked at this flooding and how high the tides were at that time. But then they started calculating and they said, no, we have to make our dikes and our protection for events that are much worse than this. So they did that. And the whole project, the so-called Delta Plan, was only finished, I guess, about 10 years ago. Then the last part was finished. What happened in the meantime? In the meantime, of course, we had this climate change. Some people don't believe in it. They should buy new glasses, I guess. But everybody who is looking at the data will agree that there is a climate change. Where it comes from, whether it's man-made or not, you can discuss on that, but you cannot neglect that there is a climate change. And the climate change will make a future flooding maybe even worse than the events that were put in the calculations to make the dikes of the Delta Plan. So they thought that they were protected, but maybe they are not protected as sufficiently as they hoped, because there are new events coming up.
But there's no way to take that into account.
No, they couldn't take that into account because this feature was not present at that time.
Well, it's interesting to understand, like, I mean, maths has helped us a lot in predicting events, but not always will they be true or will they be as accurate. And as you said, it always depends on the beginning model and what your outcome will be, right?
Can you repeat this?
No, it'll like, I'm saying that the model, like whatever model that you make, the beginning output is always what you will get for your like output. Like input and output will always the output will be dependent on your input that you give in every single model. So I think we've explored like a lot of the philosophical side of what probability shows us, and also the mathematical side, and also how these can be given in applications, and why us as students should be very like should stress on, you know, how important maths is in the future. And I'm very grateful for all of your insights, and thank you very much for the discussion today. I'm very honored and privileged for it. And is there anything else that you'd like to say before we end it?
Okay. Thank you.
Is there anything else that you'd like to say as a closing? As a closing statement.
Closing statement. Well, maybe we should continue to convince people to study mathematics and to study fundamental mathematics. Because whatever you do for applications, you need fundamentals of mathematics also. You can't do applications without knowing the fundamentals. So
But I
even in the today, when you think computer will do everything, that was very popular 40 years ago. Oh, the computer will calculate it. And nowadays, it's artificial intelligence will do it.
Yeah.
So.
But I mean, I wish that mathematics was taught more like interestingly in schools, definitely, because the way that they portray maths, a lot of students, dislike it. But if they were to teach it in a way that, fundamental maths is very important for when you grow up or like in real life in any field that you do, then maybe students would, pay more attention to it.
No, that's what we say all the time. But whether it's implemented is a different thing. We don't know that.
So on that note, thank you very much for watching the astrO podcast. And I hope to have you again on our podcast very soon.
Okay, thank you.
Thank you.